Hello all, welcome back. This is Dr. Gardner at the University of Montana. And today we're going to be continuing our review of hydrogeology and thinking about porous media. And we're going to consider the energetics of fluid in porous media. Again, I recommend that you take notes as we go and copy my notes. It'll get you writing and get your mind engaged and thinking things through spatially as we go. So grab your pen and paper if you don't have it already. And let's get started. So let's think about the energy per unit volume of a fluid. And we'll realize why this is an important measurement, but let's do some unit analysis. So energy per unit volume of a fluid. So let's do it like this. E for energy per unit volume of water. All right. And let's do a unit analysis. So units. All right. Well, energy is joules, the SI unit, over the volume of water. And joules we can further break down into, I'm going to break it down and I'll describe each of these quotients here. So kilograms mass per second squared, meters per second squared times meters, right? This is mass times acceleration, right? So that's F equals ma times distance. So force times distance equals work or energy. All right. So that's joules. That's a joule broken down. And then 1 over volume is 1 over meters cubed. So this is all just SI. We don't have to have the SI unit here, but if we simplify here, we will get a kilogram per second squared meter. All right, that guy cancels those guys, and we get kilogram per second squared meter. So I'm just going to highlight this unit, mass per time squared length. This ends up being the unit of the energy per unit volume of fluid. All right, so this is the energy per volume. Oh, I've already written that down many times. I don't need to do it again. All right, energy per unit volume. So let's recall the definition for pressure or fluid pressure. Pressure, we'll use symbol P here, at a constant density. This is important. All right. So if we have constant density of rho water, then the pressure is calculated as rho water G psi. Right, and let's that is the pressure at some point. So let's say I've got surface of my water. I've got some point down here, and I'm interested in the pressure at that point. Then I calculate it with this equation, P is equal to rho water G psi. All right, where psi is the height of the fluid above my point. All right. Let's do a unit analysis here. Unit analysis. All right. P, well, density is mass kilograms per volume meters cubed. Gravity is acceleration, so that's meters per second squared. And psi is a distance in meters. So we cancel this out. We're going to get kilograms per second squared meter. Guess what? That is our unit of joules per unit volume. So this guy is the pressure energy. We can think of pressure as the pressure energy per unit volume. This is the energy imparted on this point from the weight or the gravitational acceleration of the fluid above it. All right. So this is a form of energy per unit volume. Okay, so pressure. That is an energy per unit volume. Now let's consider the potential energy. So let's say that our point here is elevated above some datum where z equals 0. We know that in general, water wants to flow from high elevations to low elevations, or high potential energy to low potential energy. So let's look at potential energy. And recall that potential energy for constant density fluid is calculated as rho water G. And now here we use Z, where Z is the elevation of our point. And that elevation is relative to some datum. All right. The most important thing is not what the datum is, but that we keep it uniform if we're trying to compare potential energies. Well, we can do the same unit analysis. We're going to get the same thing. We're going to get kilograms per meter cubed, meters per second squared, times meters. And we're going to get the same unit, kilograms per second squared meter. So this row water GZ gives me the energy per unit volume from gravitational potential energy. So this is grav PE per unit volume. All right, let's think about some other forms of energy here that this fluid packet at this point here could have. And one is that it could be moving. So we might have kinetic energy. Okay. And this is 1/2 rho water V squared, where my V is small here. All right. And this is my velocity. Fluid velocity. All right, let's do units here. We have kilograms per meter cubed. Velocity squared is meters per second squared. So that's meters squared, second squared. All right, and we're going to get kilograms per meter second squared. All right, so this guy is the kinetic energy per unit volume. Of the same kilogram meters per second squared, this is kinetic and energy per unit volume. And these are the three main forms of energy that our subsurface water might have. And so the total energy of our fluid which we will often refer to as the fluid potential. And here I'll denote that as phi. All right. All right, our total energy is just the sum of all of these forms of energy. So our fluid potential, or our total energy, so phi is equal to our pressure, which is our pressure energy, our kinetic energy, plus our potential energy. So the total fluid potential at any point is equal to the energy imparted from the pressure or the weight of the fluid above it, from the kinetic energy, from the movement of the fluid, and from the potential energy, gravity. All right, and so I can expand this. Rho water G psi, the height of the fluid above our point, plus 1/2 rho water V squared, fluid velocity, plus rho water G Z, the height of the fluid above some datum. All right, this is an important equation. It is the total fluid potential, all right, at any point. And we're gonna now simplify this guy a little bit. So for groundwater, often, if my velocity is small, and this is true for most groundwaters. If my velocity is small, a small number squared is even smaller, all right? And my kinetic energy goes to 0, all right? Or gets really small, and basically we can ignore it. So for groundwater, we often say that the fluid potential, or the total energy, is given by rho water G psi plus rho water G Z. All right, this is the total fluid potential energy per unit volume at a point. Okay. So let's make another assumption. If let's assume rho water is constant. All right, this is a relatively decent assumption for cold groundwater. Water is pretty incompressible, and if our water remains the same temperature, we have no sort of temperature effects, then rho water constant is a reasonable assumption, and it's one that we make in groundwater. So if I do that, I can divide everything here by rho water G. All right, and this is my groundwater hydraulic head equation. So H is my hydraulic head. Psi is my pressure head. And Z is my elevation head. All right, and these are all lengths, meters and meters. And what this really important equation says is that I can take a measurement of the total fluid energy per unit volume. If I assume constant density, it is a measure of the elevation of my water above a point plus, so psi, plus the elevation of that point above some 0 datum. All right, so this is my hydraulic head. So if I had a well here, if I put a well here, all right, the water in my well would rise to this level of the water on the outside, and I could take a measurement of the total fluid energy by getting this head measurement from Z equals to 0 all the way to the water surface, or Z plus psi. It makes it very convenient for a hydrologist to measure the total energy in groundwater just by measuring the elevation of the water in the well. All right. We can break that up into our pressure energy and our gravitational potential energy. Okay, so this equation is really, can't stress the importance here. And it basically means that a hydrologist can easily measure the total energy per unit volume in their water at a point if they have a well, and they can measure the elevation. And then we can compare the total energy between points by comparing the elevation of the water in the wells reference to some datum. All right. And that groundwater will always flow from high energy to low energy, or high head to low head. All right. Okay. I hope this helped you remember the energetics of groundwater and how we can measure the total energy in groundwater. Hope you enjoyed, and I will talk to you guys later.